Hello everyone, our paper is robust online path planning for autonomous vehicle using sequential quadratic programming. All authors are with Shanghai Automotive Industry Corporation, China. Let's talk about our motivation first. In urban driving scenarios, autonomous vehicles should deal with static or moving obstacles that particularly block the roads by generating a collision-free path. Besides, path planning is required to not only consider collision avoidance, but also feasibility, that is, path is comfortable, kinetically and dynamically feasible. Such a requirement is a great challenge in urban scenarios where autonomous vehicles need to continuously wiggle through narrow passages. One typical example is shown in this figure, where each vehicle has to execute consecutive inline nudging to avoid collision. Therefore, we conclude that path planning should satisfy three requirements. First, the path should be collision-free. Second, the path should be comfortable, which means it is smooth and satisfies vehicle kinematic and dynamic constraints. Third, the path planning algorithm should be efficient enough to deal with continuously changing urban environments, and it can be executed instantaneously on autonomous vehicles. To address the above requirements, we propose a robust online path planning method. Firstly, we transform the path planning from Cartesian to frame frame. Secondly, the path planning problem is decomposed into two phases. In the first phase, a collision-free and smooth reference line is generated using quadratic programming, and it is used as initial guide in the second phase. In the second phase, the path planning problem is modeled as a nonlinear problem. Path is optimized iteratively from the initial guess. Our main contributions are as follows. We develop a novel driving corridor generation method, and our path planning method is parameter insensitive. The presentation consists of three parts, which is reference line generation, trajectory generation with constraints, and results. Now I introduce the first part, reference line generation. Reference line is a prerequisite of planning in frame frame, as it serves as bridge between map in Cartesian frame and path planning in frame frame. A high-quality reference line not only reduces the wiggling of vehicle lateral velocity and acceleration in path tracking, but also provides a good initial guide for path optimization. Therefore, in the first phase, we generate a piecewise quintic polynomial reference line by formulating an optimization problem. In the figure, an example of reference line is the green dashed dotted line. It is generated near the road center line as close as possible, and serves as the initial guide for path optimization in the next phase. Since the reference line is already collision-free and feasible, it enhances the robustness of the post-optimization. Next is detailed design. The reference line consists of M segments. We apply many relative lines rule, which means the length of each segment always starts from zero to ensure computational stability. Each segment has the same length and is expressed as nth order polynomial. The coefficients of each segment are the variables to be optimized. The objective function consists of four parts: line centering, lateral velocity, lateral acceleration, and clearance. The first term means that the lateral offset should be minimized so that the vehicle follows the center line as close as possible. The second and third term denote how quick the vehicle moves laterally, which is very important for path tracking controller and driving comfort. The fourth term is lateral offset with respect to the middle of lower and upper boundaries. The reference line is a smooth and comfortable path, and the vehicle is encouraged to follow the reference line as close as possible, so long as it doesn't violate safe corridor and vehicle feasibility constraints. In reference line generation, we only choose equality distributed control points to apply constraints. Therefore, the constraint has following four terms, namely inequality constraints of lateral offset, inequality constraints of the first and second order derivative, and continuity constraints. We consider the reference line to be third order continuous. That is to say, continuity constraints include first order, second order, and third order continuity constraints. We formalize the problem into a quadratic programming problem so that it can be fast solved by commercial software. The quadratization of the first objective term is shown in equation 1. It is an example, and the rest of the terms can be quadratized in the same way. The objective function, therefore, can be formulated in a quadratic form. The constraints can be formulated in either equality or inequality affine constraints. Now we come to the second part, trajectory generation with constraints. In this section, we discuss generation of an optimal path that satisfies kinetic and dynamic constraints in driving corridors using an efficient sequential quadratic programming approach. The optimal path consists of m segments and n-out piecewise polynomials. Many relative lines rules are also applied here. The difference is that the lengths of each pi segment are also optimization variables. The optimization problem is modeled to such a sequence of polynomial segments that minimize the following objective function. It consists of 5 parts: line centering, lateral velocity, lateral acceleration, lateral jerk, and clearance. The meaning of each term is similar to that in objective function in reference line generation. Note that although the expression of the first objective function term is very similar to that in reference line generation, it is not quadratic form due to the variable length of each segment. However, the objective function is still convex. The boundary constraints can be directly applied to each path segment in reference line generation, since all the segments has the same length. Here, the length of each pi segment is also optimization variables, and therefore the implementation of boundary constraints on the variant path segment is implicit. More specifically, there is no exact match between path segments and boundary constraints. We propose a driving corridor generation method to realize implementation of effective boundary constraints. Initial driving corridor is generated by n control points, which are equally distributed as shown in step 1. In step 2, all control points are inflated in 4 directions into cubes. In the longitudinal directions, the control points are inflated by a set length, which ensures that there's no overlap between consecutive cubes. And in the lateral direction, the inflation stops when it reaches lower or up boundaries. After optimization, we get optimized link points in step 3, which is restricted to the corresponding driving corridor. The link points are the endpoints of each segment. To consider the geometry of equal vehicle, a basic model is generated at each control point. Equal vehicle is simplified as a rectangle, and 2 cycles are added to the front and rear axle of equal vehicle respectively. A control point constraint is converted into 4 vertex constraints shown in figure 1. Nonlinear constraints are approximated into linear constraints, and the error is no more than 14 cm in worst case. As mentioned before, driving corridor constraints are applied to each link point. However, it only guarantees that the vehicle at link points stay within the driving corridor. It doesn't provide any guarantee on the safety of any other points of the path. To achieve such a guarantee, one simple way is to choose a well-designed resolution of driving corridor constraints. It ensures that the position constraints are dense enough to enforce all points throughout the path within the driving corridor shown in Figure 1. The weakness of this method is that we have to apply redundant position constraints, and therefore the computation time increases with the number of constraints, and the path can be over-conservative. We propose a novel method to enforce these driving corridor constraints. We add extra control points on those areas where path violates corridor constraints shown in Figure 2. Although the updated driving corridor constraints are slightly different from the previous constraints, we can start the algorithm using the solution of last loop so that it converges within a few iterations. Now we come to the final part, which shows experimental results. A typical scenario test is proposed to show system performance of our method. We assume that the planned trajectory is perfectly tricked. The iteration process of our proposed method is presented in the figure, which is plotted in finite frame. In the first iteration, Figure A, driving corridor constraints are applied to link points, which is indicated by origin rectangles. Collision checking is applied, and the second, third, and fourth segments fall in the collision checking. Then, in the second iteration, extra driving corridors are generated in those segments, which is shown in Figure B. Path is regenerated with the newly added constraints, and the same process is repeated until all path segments pass the collision checking test. We compare off method with minimum snap and piecewise jerk method. We simplify equal vehicle as a point and only study the quality of generated paths of each method. The velocity, acceleration, and jerk are also calculated to qualitatively indicate the path quality shown in right figure. We calculate the mean and maximum absolute value of lateral offset, velocity, acceleration, and jerk of the path in each method, and we summarize the data in left table. The right data denotes the better one, and off method generates better paths than minimum snap method. Then we study the parameter sensitivity between off method and minimum snap method. Minimum snap method depends heavily on cost function parameters. While 20 parameters can perform well in some scenario, while it can result in completely different performance in other scenarios. Our method systematically deals with this issue by adding the length of each polynomial segment as augmentation parameter. According to this figure, when using two sets of completely different cost function parameters, the path of method doesn't change too much by adjusting the length of each polynomial segment. The two blue paths almost overlap. While the path that generated by minimum snap method varies greatly, there are apparent differences between the two red paths. That is the end of the presentation. Thanks for your attention.